NMR, or nuclear magnetic resonance, is a spectroscopic technique which allows for molecular structure determination along with sample identification and purity analysis, among other things. Although both proton and carbon-13 NMR are more commonly used, NMR of other nuclei are also routinely conducted. In this video presentation, we will further explore the concepts behind NMR spectroscopy of nuclei other than proton and carbon-13.
Many nuclei spin about an axis. This inherent property of nuclei is a representation of the total angular momentum of a nucleus. Due to their electric charge, the spin of nuclei results in the generation of the magnetic moment. The magnetic moment is related to a spin of nucleus by the gyromagnetic ratio, which is a proportionally constant unique to its nuclei.
For a nucleus in which the number of protons and neutrons are even, the nuclear spin is zero, and as a consequence, the magnetic moment is also zero. Examples of these are carbon-12 and oxygen-16 isotopes of carbon and oxygen, which are invisible in NMR as they do not have magnetic moments, as they both have a nuclear spin of zero respectively. Other nuclei, such as deuterium and nitrogen-14 isotope of nitrogen, are NMR active as they have non-zero magnetic moments. However, the nature of their nuclear spins makes NMR analysis more difficult compared to hydrogen and carbon NMR.
This table shows some nuclei of different spins, both zero and non-zero. Other properties such as natural abundance and gyromagnetic ratio are also highlighted, which all influence NMR sensitivity.
When a nucleus with a non-zero spin is exposed to an external magnetic field, the degenerate energy levels of the ground state are split, as a nucleus is able to have more than one energy level. The resultant energy levels are occupied by spins which align either with or against the magnetic field, respectively. The detection of these absorption signals forms the NMR spectrum.
The sample is dissolved in a solvent, usually chloroform, and placed in a magnetic field. A radio frequency generator then irradiates the sample with a short pulse of radiation, causing resonance. When the nuclei fall back to their lower energy states, the detector measures the energy released and a spectrum is recorded.
When considering NMR analysis of nuclei, some factors which influence NMR sensitivity are: number 1, spin. The charge distribution of quadrupolar nuclei are uneven, and the lifetime of their magnetic states are shorter, making NMR measurements difficult due to broadening of lines. Number 2, isotopic abundance. 100% isotopic abundance compared to low abundance of nuclei gives higher NMR sensitivity, as is shown by this diagram. And number 3, gyromagnetic ratio. A higher gyromagnetic ratio means greater NMR sensitivity due to a higher magnetic moment, resonant frequency, and high rate of precession, which all lead to a stronger NMR signal.
For the remainder of this presentation, we will focus further on 19F and 31P isotopes of fluorine and phosphorus. The properties of both nuclei make them sensitive for NMR spectroscopy, producing clear, sharp NMR spectra.
Fluorine-19 NMR is an analytical method used to identify fluorine-containing compounds. Fluorine-19 has a nuclear spin of a half and a large gyromagnetic ratio, which means that this isotope is highly responsive to NMR measurements.
Chemical shift of organofluorine compound range from 50 to -250 ppm. Factors influencing chemical shift are 1. Solvent. The variation in fluorine chemical shift is around 1 ppm. 2. Isotopic. A change in chemical shift can be observed when a nearby atom is replaced by an isotope such as carbon-12 or carbon-13. Number 3. Steric deshielding occurs if there is a direct overlap of the van der Waals alkyl group and the fluorine.
Fluorine coupling is influenced by the spatial arrangement and the number of bonds between a coupling partner atom. The fluorine-fluorine coupling values range between 250 to 300 Hz. Proton-fluorine couplings are around 50 Hz, while fluorine-carbon coupling ranges between 1 to 45 Hz depending on the splitting types.
Fluorine-19 spectra usually first order in the multiplicities due to the wide range of chemical shifts. For example, the spectrum shown in a mixture of 2 fluorine-containing compounds, 3-fluorotoluene TFT and 3-fluoroethanol. The fluorine-19 spectrum of T80 appears as a strong single peak with chemical shift minus 63.72 ppm. Structure consists of 3 equivalent F nuclei. The fluorine-19 spectrum for 3-fluoroethanol is split into a triplet at minus 77 ppm. The fluorine-19 nuclei couples with the proton nuclei on neighboring carbon atoms in the molecules.
The applications of fluorine-19 include number 1, drug analysis. The detection of fluorinated materials used as drugs has been demonstrated, such as 5-fluoroacyl, an anti-cancer drug. Number 2, fragment-based drug discovery. Fluorine-19 NMR can be used for screening the fragments, assessing competition among the fragments, and identifying the binding.
The 31P isotope of phosphorus is very useful in NMR spectroscopy due to its relatively high gyromagnetic ratio, which is in between that of proton and carbon-13. It also has a 100% isotopic abundance and a spin of half, which make its NMR spectra relatively simple to interpret.
The chemical shift of phosphorus-31 in diamagnetic compounds ranges between minus 200 to 200 ppm. While proton NMR is referenced to tetramethylsilane, 85% phosphoric acid is typically used as an external standard in phosphorus-31 NMR. Phosphorus-31 NMR chemical shift is influenced by the electronegativity of the substituents, the pi bonding character of the substituents, bond angles, and solvent.
Due to the dipolar nuclei, there is a spherical distribution of positive electric charge of the electromagnetic field, giving rise to a strong, sharp NMR as shown in the diagram. Similar to carbon-13 NMR, 31P spectra are typically done with all proton signal decoupled. However, if considering 31P proton coupling, proton P coupling values can cover a wide range and decrease as shown.
Some common applications of phosphorus-31 NMR include, number 1, assaying sample purity. It is possible to differentiate between compounds containing phosphorus, for example, between the starting material versus the products, using phosphorus-31 NMR. Number 2, monitoring reactions by tracking changes in phosphorus-31 peak intensity at different time intervals using NMR. An example of this is shown in the diagram, which shows the reaction of a phosphorus ligand with a metal complex. The initial peak corresponding to the free ligand shrinks as the reaction progresses, while the new peak corresponding to the formed product grows in intensity.
Another application of 31P NMR is the analysis of biological macromolecules, many of which include phosphorus, such as DNA as pictured. 31P NMR can be used to analyze both conformation and dynamics of such biological macromolecules.